Hello, in the last video we discussed about context-free languages and showed that a language is context-free if it's designed by a context-free grammar. So for each language, if we can write a context-free grammar that generates all the strings of this language, we can in this case say that the language is context-free. Let's take the set of all strings that can be written as WW reverse. This means that all the strings that will be accepted will be in the form AA and then AA, for example. The first part is AA and the second part is AA since it's the same as the first part but reversed. Another example, if the first part is A, B, A, B, another A, B, for example, there should be a second part for this string, which is BA, BA. The reverse of this part is BA, BA. So in this case, we will accept the string. Another example that starts with B is the following. We can write BA, then B, and we will reverse now, we will write BAB. So all the strings that will be accepted have this form, okay? In order to write a grammar for these strings, we need to find some pattern. We need to find an idea how to decompose this string into parts and how to write simple rules to generate all the strings of this type. If we have an A here, in the last position also we will have a symbol A. If we have A, we will find A, and if in the example we have B, at the end we will have to see a B, okay? And for the string in the middle, we can say that it follows the same pattern as the original string, and for it, the first symbol should also appear at the end, okay? For the second string, for example, if we have B here in the second position, we also have to find the B in the second to the last position, okay? And at every moment, we are decomposing the string into three parts, okay? Suppose that this is a string S. We will decompose it in three parts, where the part 1 should equal the part 3. So if it's an A here, at the last also we should find an A. If it's a B in the beginning, we should find a B at the end. And in the middle here, we will say that this is a string also that we will analyze just with the same manner as the first string. So we will write here each string will be changed by A, another string A, or B, another string B. Okay, for example, for this string here, we will say that S will produce A, S, A. Okay, so this A appeared and the last A also appeared, and this S should lead to the AA in the middle. Okay, so we can write that this also produce ASA, and we will write the A in the beginning and the A at the end. Okay, and for the last S here, since for the string here all the symbols have appeared, for the last S here it should be changed by epsilon, so that we will write that this will produce the string AA, AA. If we change the S by epsilon. So we can add the rule here, or epsilon, to this grammar, and we can prove that this grammar works for all the strings. We can generate all the strings of the form WWR. Let's take this example, okay? To prove that this is a correct string, we have to prove that it can be generated by this grammar. Let's try to prove this by drawing a parse tree for the string. So for the parse tree, we'll start with S, and since it starts with the letter B here, we will choose this rule. So S will produce 3 symbols, B, S, B. Okay, so this B appeared, also the last B appeared here. So this S should lead to AB, BA. Since we will start now from A, we will choose this rule, and S will produce ASA. And now this A appeared, and also this A appeared, and we should focus on the middle here, which is the substring BB from this S. So we'll again apply this rule. We will say that S produces B, S, B. And now, since all the symbols have appeared in this parse tree, we can say that the last S here will produce nothing. It will be the epsilon according to this production. And this will be an example of context-free grammar for the language of the strings on the form WW reverse.